Okay, Dave, this proton is also the atomic number. Okay, on your periodic table, that's the number. Hydrogen's number one, it's one proton, right? Helium's number two, it's two protons. Carbon's number six, that's also six protons. So that's a critical number, and the reason, as you'll see, is it's critical because that's what holds the number of electrons. That's what determines how many electrons there are. Okay. So we look at here number two. Let's see, and I think it was Goldstein that discovered this. That gets credit for this. Goldstein, S-T-E-I-N. If you look on your PowerPoint, you'll see the date. I think it was 1906 or something like that, but I forget. Anyway, the next one here. Let's see, the neutron. The neutron, I believe, was what was his name? Chadwick. I believe his name was Chadwick. Okay, Chadwick, and I forget, but he was actually later than the rest. I think it was 19. I forget what it was. It was 26 or something, or 16. It was a long time. But anyway, the neutron together with the protons equal the atomic mass. Okay. That's the atomic mass. And the neutron was the last one to be discovered. It was a little bit weird. The electron was the first, but they knew the total atom wasn't negative, so they must be positive, and the electron didn't contribute to the mass, but the proton only contributed to half the mass, so this neutron was a mystery. And so this one was discovered a little bit later, and the difference in neutrons is what makes isotopes. So you put this zero here, the symbol is this little lowercase n, and you have a mass number of 1, and the proton number is 0, and the charge is 0. The proton would look like this. It's got a p, it has a 1 there for the atomic number of protons. It's got 1 there for a mass, and it's got a 1 plus up there for the charge. Okay. And the electron, of course, is electron has got basically a 0 charge here and a 0 mass here and a 1 negative there. Okay, and this guy is Thomson, and he is 1897, I believe, and that's the cathode ray. Electron's the cathode ray. Okay. So now the guy here this is Rutherford. Okay, the nucleus. This is Ernst Rutherford. And this experiment was 1911, and what he proved was that the nucleus was, he did it. This is the gold foil. You got to remember this gold foil experiment, and she does a good job in her PowerPoint showing this. But the nucleus, when you think Rutherford, you think nucleus, and what he showed was, first of all, there is a nucleus. There is a nucleus, and it is positive, and it is incredibly small and therefore dense. Remember, the nucleus is calculated, the atomic nucleus is calculated to have the density, like a pea would be like a green pea having a mass of 1,000,000 tons. It's like incredible. Now this alpha particle, I don't know why she's got this thing in this order. I'm not sure, but an alpha particle is what Rutherford shot at the nucleus, and so it's a helium nucleus. Well, a helium has 2 protons, okay, and it has 2 neutrons. Okay, that's what's in the nucleus. Okay, that's the helium nucleus. The electrons are stripped, so it's got a 2 plus charge. That is an alpha particle. Okay, and that's what Rutherford shot at the gold foil in his experiment. Okay, the atomic number, boom, is nothing but the number of protons. Okay, an isotope is depends on a different number of neutrons, different numbers of neutrons, and therefore different masses. Okay, because remember, the mass is made up of, I think I said it here, the protons and the neutrons, okay? So if you have a different number of neutrons, you have a different mass. You can't have a different number of protons. If you have a different number of protons, you have a different element, okay? Well, here we go, mass numbers here. The sum of the protons and the neutrons. And it's also, I don't know about this nucleon number. I'm not familiar with that term, but atoms with the same number of protons but different numbers of neutrons are called isotopes. Okay, same number of protons, different neutrons. Those are called isotopes. Now, all of the masses you see on the periodic table, those are averages. Averages of what? Averages of all known, you know what I'm going to say, isotopes. Okay, so every element, if you take a sample of any element, you know, a common element like carbon, if you take a sample of pure carbon or pure oxygen or pure hydrogen or pure anything, you will have a certain percentage of isotopes, different isotopes. In other words, elements with the same number of protons but different numbers of neutrons. And so that mass you see on the table is the average of all the isotopes. That's what you got to remember. Okay? Alrighty, I'll be right back. Okay, well, here I think we talked about average atomic mass, and every sample of any pure element is going to have different isotopes in it, and that's why it's called the average atomic mass. That's why the numbers on the periodic table are not even. Okay, so you take all the isotopes, and the way you get the average atomic mass is you take the percentage, and you multiply it by the isotopic mass, okay, and then you add those up. So you take the sum of the isotopic masses, okay, you take the sum of the percentages of the isotopic masses, and that will equal the average. That will give you the average mass. Okay, and so the sum, when you add the percentages up, you'll get a total of 100%. When you add the isotopic masses up, you'll get the average mass. Okay, so energy levels. Now this is a tricky subject because it depends on whose model you're looking at, but the simplest is Bohr's model. If he takes that's the nucleus, then you got these different energy levels. That's the first energy level, second energy level, and the third energy level. Well, the quantum mechanical model disputes this in terms of the shape of the energy levels. It doesn't dispute the fact that we have different energy levels. This is n equals 1, n equals 2, n equals 3, and so on and so forth. N equals 4, okay? So the quantum mechanical model doesn't dispute Bohr's model. This is Bohr's model. And we still use it right now to talk about this in the simplest forms, okay? But what does this say? It says specific quantized values of energy that an electron can have in an atom. Well, Bohr's the first one that came up with this, and he came up with this, you know, with his bright line emission spectrum, saying that if you had an atom here, if you had a hydrogen atom, and so you subject it to electrical subjected to electrical current, you might take this, you know, it's only got an electron in the first energy level, but you might be able to excite that electron up to here, and then what happens is that electron is going to fall back down, okay? And so when this electron jumps up to this energy level here, energy is absorbed, and this is the excited state. And this is coming up later in the study guide, I think. But when the electron drops back down here, energy is released. And that's what equals the wavelength of light. Okay, that's what gives you the different wavelengths, okay? So then down here is the ground state, where the electron came from, and where it got excited to up here at the high stage. That is the excited state. Okay, so what that amounts to is then somehow you figure out a way to excite this electron up to a higher energy level. That's the excited state. That means it absorbed energy. When it falls down from the excited state down to the ground state, then it releases energy. And that energy that's released is correspondent to exactly one and only one wavelength of electromagnetic radiation. If it falls in the visible spectrum, we see it as a different color of light. Okay? Now, the interesting thing is in the quantum mechanical model, and it's funny to me that she's putting these, she sticks these all in here. I'm trying to get rid of these, clean this up a little bit. She mixes this up in here together. I mean, you know, like number 10 and number 11. But anyway, just as well, the quantum mechanical model is the first one to come up with this idea of sublevels. That's what number 11 is talking about, sub-energy levels. Bohr didn't have that idea. Bohr had this energy level that was 1 or 2 or 3 or 4. Well, the quantum mechanical guys, they said, okay, well, within each energy level there is a first sublevel. In the first energy level, that's all there is just the sublevel, okay? And that first sublevel is always S, okay? That's S, okay? But then in the second energy level and every level thereafter, there is an S sublevel. And then after the S sublevel, there are the P sublevels, okay? So the P sublevels come out here like this, right? And so the bottom line is, if you were to draw a circle around, say, in the second energy level, the outer tips of these P sublevels, that would still be the second energy level. But what you have then is energy level 2 sublevels. You got S and P. You've got one S orbital and 3 p orbitals in the second energy level, and those are the energy sublevels. Now remember, each orbital can only handle 2 electrons. So the S electron down here, S2, or 2s, has got 2 electrons. 2px has got 2 electrons. 2py has got 2 electrons, and 2pz has got 2 electrons. That's a total of 8 electrons. So then we go to the third energy level. That would be this one right here. So the third energy level, okay, it's got an S orbital, just like the previous one. It's just outside the 2s, right? And then it's also got its p electrons. And see, and they're coming out there and they're reaching just this outer level of the third energy level, okay? So if you drew a circle around the tips of these p orbitals in the 3, it would look like, again, it would start to go back and look like Bohr's orbital. But what you have here in the third energy level is, where's my green one? Here, my green, this would be 3s right here, and then these would be 3p, 3px, 3py, and 3pz, okay? And that continues on and on and on and on. You look in your book and you'll see it, and after you get to the D level, it gets so complicated in here that you can't even make sense of it. But that's what these sublevels mean, okay? And that's the quantum mechanical model that came up with the sublevel idea. Bohr stopped at the energy level idea, which was a revolutionary idea. It shook the world. And, you know, they were all reluctant to believe it until he showed them with his bright line emission spectrum. He said, yeah, well, how do you explain that we only get this color of light? And it corresponds exactly to the energy difference between his projected energy levels, okay? So anyway, we talk about orbital here. An orbital can contain only 2 electrons, and there's always a trick question. How many electrons can, you know, d orbital contain? And everybody wants to say 10. No. The d sublevel can contain 10 electrons. An orbital in the d sublevel can only contain 2. An orbital in the any p can only hold 2. Any orbital can only hold 2 electrons. Whether it's 1s, 2s, 2p, 3s, 3p, 3d, 4s, whatever. An orbital can only contain 2 electrons. And it can only contain 2 electrons if they have opposite spins. I haven't heard anything about that in your text, but anyway, that's important, okay? All right, so we go down here. Now we go down here to boom, 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 right here. All right, so I think we just went over this excited state and ground state and whatnot. Okay, the excited state is when an electron goes from, so let's say we've got these energy levels, boom and boom. Okay, so we'll say this is the ground state. An electron, I'll use a different color. An electron gets zapped, boom, and it gets zapped up here. And so this is the excited state. Okay? State. Okay? Now, eventually, it's going to fall back down. When it falls back down, it goes from the excited state back down to the ground state. Here, energy is absorbed. Energy has to be absorbed to send it up to the excited state. Here, energy is released. Okay, so as it goes from the ground state to the excited state and back from the excited state back to the ground state. Okay, from the ground state to the excited state, energy absorbed. From the excited state to the ground state, energy is released, and that's what gives you that bright line emission spectrum. Okay. Now, cation. Great example is sodium. Okay, sodium, it's got 11 protons. Let's say it's got 12 neutrons and 11 electrons. Okay, so when sodium bonds, what happens is it gives up one electron and the sodium becomes positively charged. That is the sodium ion. Okay, you don't change the name of it. That's the sodium ion. Magnesium would, when it bonds, what happens to it? It gives up 2 electrons, so it becomes 2 plus. Okay, so this is the magnesium ion. This is the sodium ion. A cation is an ion that loses electrons. An anion, chlorine, is a great example. So chlorine, because it has a high electronegativity, gains an electron, and it becomes, now you change the name, change the ending, it becomes an IDE ion, okay, a chloride ion. All right, oxygen gains 2 electrons, okay, and it becomes an 2 negative oxide ion, okay. So an atom that gains electrons becomes an anion, becomes negative. Atom that loses electrons becomes a cation, it's positive. Okay, you don't change the ending there. Okay. Now, what are the valence electrons? We already know those are S and P sublevel electrons. How many are there? 8 total. Okay. There's 2 in the S and a possibility of 6 in the P. Okay, that's where the octet rule comes in, and we'll be looking at that in just a second. Okay. All right, so this seems like it's jumping around a little bit, but you really need to look at this girl's PowerPoint. It's good. It's good. Okay, so let's see who we got here. Boom, boom, boom. The following scientists: Thomson, electron. Okay, Goldstein, proton. Millikan, you think oil drop, and he is the one who calculated, I believe, the mass, no, the charge of the electron. Charge of the electron. Thomson related the mass of the electron, a relationship between the mass and the charge. Okay, so Goldstein's the proton, Thomson's the electron, Rutherford is the nucleus. Remember, I showed you up above the 3 things. Nucleus. First of all, the most important thing is that he showed there is a nucleus. Number 2, it's positive. And number 3, it is incredibly small and therefore dense. Okay, Chadwick is the neutron. Remember, that's got a 0 charge, 0 protons, and a 1 mass. Bohr think energy levels. He's the first guy to come up with the idea that they were energy levels. Schrodinger, you think quantum mechanical model. Now the difference, I think I may have erased this up here. I think I did. The difference between Bohr's model and the quantum mechanical model is the fact that the quantum mechanical model is based on mathematics, calculus, basically calculus and statistics. And remember, it introduces the idea of sublevels. The quantum mechanical model said that you can't predict where these electrons are. See, Bohr tried to say they acted like objects that we're familiar with, like planets orbiting around a sun or whatnot. And these quantum mechanical guys, Schrodinger, Max Planck, what's his name, Heisenberg, all these guys, what they said was, okay, we agree that these electrons have different energies, but they're not in concentric circles. They're not circling that nucleus like a solar system. Okay, they're going everywhere they can possibly go. The deal is with the place where we agree with Bohr is they can only go out so far, and that's determined by how much energy they have. They also change the shape of these things based on calculus and probability and statistics and so on, so they don't look like these round circles anymore. The first orbital in every energy level is the S, circular, and then the second three energy levels are those SP or the P, X, Y, Z orbitals, right? And then the D's get all complicated. So that would be the second energy level. Third energy level, again, it's got 3S, and then 3P, 3px, 3py, and 3pz. So they change the shape of these orbitals, and they call them electron clouds, and it's based on where an electron could be found 90% of the time. Okay? So Goldstein, and you have to look this up, but Goldstein is the guy, the positive rays. Okay? The positive rays, what are the positive rays? They're protons. Okay? And that's his deal. Okay? All right, so this is going to disappear. So here we go. Boom, boom, boom. So we've done this. All right, let's see. Where are we here? Thomson, cathode ray. If you think of Thomson, you think cathode ray. Okay? And the cathode ray is simply a stream of electrons, and as they get excited and move across from the negative to the positive pole, what happens is they give off energy as they lose energy, and they give off a certain color of light. And that's the whole thing with Bohr. He looked at that light through a prism, and what he saw was not like the rainbow, not the whole rainbow. He only saw distinct lines. But Thomson's the cathode ray, and I believe that's 1897. Rutherford, I remember, is 1911. Okay, same year as the Colt 45. Automatic, Colt 45 automatic, 1911. Anyway, so Goldstein, we said again, is the proton. You have to look up his date, but he's the proton. Millikan, through that oil drop thing, and what he did is he got this charge to mass ratio, okay, and he determined the charge of the electron. Okay, Thomson, remember, related the mass to the charge. Millikan actually identified the charge. Okay, Rutherford, again, the answer is nucleus. If the question is Rutherford, the answer is nucleus. Number one, there is one. Number two, it's positive, and number three, it is dense. What do you mean dense? All of the mass is in that tiny, tiny nucleus. Okay, that's what it means when most of those alpha particles didn't hit anything. That proved that nucleus was tiny, and that's where all the mass is. So they calculated how small it was and how much mass was in it, and it comes out to the idea that a green pea would have a mass of 1 times 10 to the 6 would be a million. 1 times 10 to the 8, 100 million. 100 million tons, the size of a pea. Okay? Now, Chadwick is the guy, 1932, see, that's much later, but he's the neutron. Remember the symbol for the neutron? You got to remember this. That's a lowercase n. He's got a 0 there for his proton charge, right? He's got a 1 there for his mass charge, and a 0 up here for his charge, okay? I don't mean a mass charge. That's his mass number. 0 is his atomic number. Atomic number equals proton, so they're none. Mass is 1 and no charge because the neutron has no charge. Okay? All right, so you need to go back and think through that. It takes a little while. Now, Bohr is a very, very important guy. He came up with huge information to these guys. And these mathematicians, these eggheads, they were truly eggheads, these Schrodinger and Einstein and all these guys. But Bohr is the guy who said electrons aren't out there in that plum pudding model. They exist in certain energy levels. Remember, Dalton and all the way back to Democritus said atoms were little tiny particles. And then you had Thomson, and he said, well, I don't know about that. You might have little tiny particles, but in that particle you got negative charges, right? And because the total thing is neutral, you must have positive charges, right? Negative and positive charges. So that gave you this plum pudding model. Chadwick up above, he said, well, the number of protons doesn't equal the mass of the atom, so there must be some neutral charges in there, right? And so what Rutherford did is he said, okay, boys, I agree with all that, except I can tell you right now, all the protons and the neutrons are in that nucleus, and the electrons are out there outside, okay? Nothing but the electrons out here in this area. Well, Bohr said, okay, the electrons are out there. I'm with you there. I can deal with that. But they're not out there helter-skelter. They're out there in specific energy levels. And then the quantum mechanical model came along and said, okay, well, these electrons, they're out there, and they're at specific energy levels, but them energy levels are not concentric circles, okay? So you call that 1s, and then 2s, and 2p, and then 3p, and the shape, and it gets bigger and bigger and bigger and bigger. But if you draw a circle around the outer edge of all of them, you go back to this concentric circle idea, okay? Now, Schrodinger, what do we say about Schrodinger here? Yeah, here we're talking about these different. You see, this is after Chadwick with the neutrons, but see, he used this highly mathematical and statistical model that showed these weird-looking shapes for these orbitals. Okay, and this is more with Millikan. Let's see what we got here. Millikan, doom ba doom ba doom, and doom ba doom ba doom. Okay, you're gonna just have to go through that. PowerPoint she's got. All right, but now we look at old Mendeleev. Let's see, what's the date on him? You need to get the date on him. I believe this is like 1860s. I'm not sure, but it's pretty early. But the thing that Mendeleev did, you see, all these guys at this time, starting from Dalton on, Dalton was 1808, but they all had them in order of mass, and they were getting pretty good at getting the mass of these atoms. But Mendeleev said, I'm going to line these babies up in order of properties. Mass will come second. Mass is important. But if I'm going to line them up so the properties line up, and that may give me a little few screwy ideas with mass, but I'm going to make the properties line up. And so what he was looking at was things like argon. If you look at argon, and potassium. What's potassium? Yeah, argon and potassium. Their atomic masses are mixed up. They're confused. And so Mendeleev looked at that and said, well, if I go according to atomic mass, I'm going to have this damn noble gas over there, and he's going to be in the same column with group 1, where I've got all these highly reactive metals, and I'm going to have an unreactive gas right there in the middle of them. So screw it, I'm not going to do it. I'm going to put argon back over there with the group 18 over there with a group of noble gases which are completely unreactive, and I'm going to put potassium in a group with the highly reactive metals, which it is, and let the damn mass, we'll work the mass problem out later. Well, it ended up he was right. He was correct. And what he did is, when he put his thing together, he ended up having little gaps in his table, and before they could all get together and go meet wherever they were going to meet in Switzerland or wherever they met, scientists started showing up, and they found the elements that fit right in the hole where he said they would, and he predicted their properties, and he was right. So they said, whoa, that old Russian guy's got it together, and so they stuck with Mendeleev's deal. But the big thing is he subordinated the mass to the properties. That's his big deal. Everybody stuck with mass up to this point, and then Robert, what's his name? Oh shoot, what's his name? He came along. The next thing was he came along and he lined them up by atomic number, and that's how they're lined up now, as atomic number of protons, not mass, but atomic number. That's how they are today. Okay, but you know, Ms. Green has got a good. She's got a good bunch of information on the PowerPoint. You should look at that. Okay, Mendeleev's table. Let's see. Be able to identify elements in the following groups and categories and whatnot. Well, look here. Let's see. If you look at this periodic table, okay, this is group 1, okay. These are the alkali metals. Group 2, these are the alkaline earth metals. Okay, now these, as you know, I hope, all the way over here, these are the transition metals. This is the D block. This is together. This is the S block, okay? This is the P block. Okay, so we're going to call this group 1, 2, and now they switch this to 13 and 14 and 15, 16, 17, and 18, so on and so forth. But everything along here, now this thing comes along here like this, and this stair step I'm making here, everything here is metals. All the way back here. Okay? And only this area up here is nonmetals. These are the noble gases, okay? Group 18. Group 18 are the noble gases. Alright, and these elements right here, on this side, right along this stair step, these are the metalloids. They have properties of both the metals and the nonmetals. Okay? When these elements bond, they lose electrons. Metals lose electrons. These are all positive. Here we can say group 1 is always 1 plus, 2 is 2 plus, 13 is 3 plus, 14 doesn't usually form ions, okay, so we leave it alone. 15, this is the nitrogen family, tends to gain 3 electrons, so it's usually 3 negative. This is the oxygen family, it's 2 negative. This is fluorine, it's 1 negative. And these babies don't bond, okay? These are the noble gases, they don't bond. Alright? Now when I flip back here, what we're going to do is we're going to end up erasing this, but anyway, so we go back here, okay, energy level, where are we? Be ready to identify the elements, categories, metals, nonmetals, metalloid, alkali, alkaline earth, transition, halogens, noble gases, inner transition. Well, let me go back to that and make sure we get that straight. All right, so we lost it. So we said this is the halogens, okay? There we go. These are the halogens. These are the nonmetals. These are the metals, okay? These are the alkaline metals. These are the alkaline earth metals. This whole box right here, one through this 10 block thing right here, these are the transition metals. These are inner transition. And what is it I missed? Metalloids, let's see. Alkaline metals, alkaline earth metals, inner transition, noble gases. Oh, halogens. The halogens are here. This group 17, they get their own name. Halogen means salt. Okay? They get their own name here. It's also, and by the way, you can name any group by the top metal in it. This is the carbon group. This is the boron group, nitrogen group, oxygen group, fluoride group. This and these have names. I forget what the names of them are, but usually you just call them nitrogen group, oxygen group, fluoride group. But the fluorine group is also called halogens, and that means salt. Okay, because when any of these elements bond with any of these metals, it forms an ionic compound always. And an ionic compound is a salt. So they're called halogens. Okay? Alright, so let's go back over here. Let me drop this down here and see what happens. Alright, so let's see. Do we get that straight? So we got transition metals, halogens, noble gases, inner transition metals. Okay? And then she's got some questions noted here. Okay? Alright, so we know the major components of Bohr's model. Alright, so the electrons are in a particular path and a fixed amount of energy. They do not lose energy as they travel around the nucleus. Yeah, and that's kind of spooky, but anyway, the energy level is the region around the nucleus. Remember, Bohr, when you think Bohr, oh my God, what do I have to do there? When you think Bohr, I gotta get rid of this thing. Alright, where am I get out of that? Alright, here we go. When you think in between electron levels to move from one electron to another, they must gain, lose specific. Well, this is back to our thing. Okay, there's the nucleus, energy level 1, energy level 2, energy level 3, energy level 4. He won the Nobel Prize because he is the first one to identify the fact that these electrons did not exist out here helter-skelter. They existed in specific energy levels. All right, so let's see. Now, he pictured it as like a, circling around the nucleus like planets around the sun. Okay, and we know that that's not true. But he says these electrons can jump from one level to another, but they're going to have to absorb energy to go up there to a higher level, okay? And when they absorb that energy, they're not going to keep that energy forever. So eventually, they're going to fall back down, and they're going to fall back down to the lowest available energy level. Here, they absorb energy. When they fall back down, they give off energy, okay? So this is the excited state. This is the ground state, okay? Let's see what else we got going on. Yeah. Move from one to another, they gain or lose specific amount of energy. And that's the whole key with the bright line emission spectrum. They gain exactly enough energy to go from this energy level to this energy level. And then when they drop back down, they lose exactly that amount of energy. And that was the key to Bohr's thing. He said that exact amount of energy would produce, say, a red streak of light. And that's what you find when you look at the bright line emission spectrum of those elements. And they match up perfectly. It was really kind of scary the way he did it. It's one of the beautiful things in science, the way he made that prediction. But anyway, let's see here what we got here. Let's go down here after Bohr. Come down here. Know the major components of the quantum mechanical atom. Okay, the main thing about the quantum mechanical thing, atom, is this. The number one thing you want to remember is this right here. It's based on, where does it say? It's going to say, based on, whoops, that's Bohr. It was based on, you call it Bohr's model, you call it the planetary model. The quantum mechanical model is based on, let's say it here somewhere. Well, anyway, the quantum mechanical model is based on mathematics, and statistics, and probability. Very complicated and very, she says here, what does she say? It's not few analogies in the visible world. It is not something that's easy to visualize, okay? So the quantum mechanical model does not define the exact path. In other words, you can't talk about orbits or whatnot in the quantum mechanical model. The quantum mechanical model says, okay, here's the nucleus, and says the electrons exist out here like this. And they're going to exist everywhere like this, okay? And then when you add more and more electrons, then they're going to try to come out here on the outside, okay? And then they're going to separate themselves like this, and they'll separate themselves like this, and they'll separate themselves like this, and they'll separate themselves like this. And so that's where we get this idea of these p orbitals like this, okay? S and p orbitals, these strange shapes. It's based on calculation, okay? All right, so what we got here? Boom, 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 certain position. Heisenberg said that you can never predict both the position and both the location and the velocity of the electron. One or the other. You can't do them both, okay? Now, this seems like it's sort of out of place here, but identify the period number and the group number for any element. Well, let's go back here to this thing here. I'm just going to screw this up. Okay, so these numbers are the period numbers right here. Okay, the periodic table, I don't know why I can't straighten this out. So this would be, maybe I have to do it like this. Okay, so this would be period number 1. This is N, okay? Whoops, it's not uppercase N. It's a lowercase n. And you know, N equals energy level. And that equals the period. Okay? 1, 2, 3, 4, 5, 6, 7. And those are the periods, okay? These are the groups. 1, 2, and then the new period, the modern periodic table does 4 through 10, 4 through 12 here. And this is 13, 14, 15, 16, 17, 18. These are groups. These are periods. Okay? These also, by the way, are called families. And they're called families because the elements in any given group have similar chemical properties. And the reason they have similar chemical properties is because they have the same number of valence electrons. Okay? So let's see what was after that there. So it said identify the group number, boom, boom, group numbers for any elements. Be able to find the number of valence electrons for any element. Well, let me see if I can go back to that. That'd be great if I could get back to that. There we go. So this table like this is nice because every element here has one valence electron. Every element there has one valence electron. Okay, so we'll use X for the element symbol. That'd be hydrogen. This would be lithium. Okay, this would be sodium and potassium and so on and so forth. So we use X, okay? Every element here has 2 electrons. Come on, god damn it. 2 electrons, okay? 2 electrons. 2 electrons, okay? And I'm putting them in the right place too. Now every element, well, I always say the elements in group 13, now look, they stretch out like this. Why do they form a pyramid like that? Because the electrons repel each other. So they stretch out as far as they can. This is 120 degrees, this is 180 degrees. And when this thing bonds, it would be 180 degrees because that's where it would bond, right? Now, look at carbon. The carbon is going to snap back. It looks like 90 degrees, but it's not. This is called a tetrahedron. That's 109 degrees. Now we go to nitrogen, and look what happens. We got to pair 2 up, and we pair them up here, and those paired shares push these other 3 down. Okay, that shape right there is called a pyramid, okay? We look at oxygen, and oxygen has 2 pairs up here that are paired up like this, and so then it's got 2 lonesome electrons down there, okay? So this one it would be form a linear bond. Of course, it'd be ionic. This would be linear, it'd be ionic. Now this one is triangular planar, 120 degrees. This one is called tetrahedral, 109 degrees, okay? 109 degrees. This is 120 degrees. This is called pyramidal, okay? Pyramidal. This says 109. So this is tetrahedron. This is called triangular. This one is called pyramidal. And so these angles are equal, but these are not because you got this unshared pair here. That's the VSEPR theory, and that pushes down harder than these single electrons. Here with the oxygen, you have 2 unshared pairs. So this one's just called bent. Now with the halogens, you have 3 unshared pairs. So they snap back into more reasonable looking shape. So they pair up like this. I shouldn't have put that one there. I'll put that one here. So they pair up like this. So you got 1, 2, 3, 4, 5, 6, 7. There's your 7th electron. Of course, in the noble gases, now they have all 8. All of them are paired up. They don't want to gain electrons. They don't want to lose electrons, and that's why they say they're inert. This guy needs 1 to have 8. Okay, that's why he forms a 1 negative bond. This guy needs 2 to form 8. That's why she forms a 2 negative. This guy needs 3 to form 8. That's why he's 3 negative. This guy is always trying to either gain 4 or lose 4, but it never can gain them or lose them because it's right in the middle. His electronegativity won't work. This guy is a 3 plus. He loses all 3 of those. This guy is a 2 plus. He loses both of those. This guy is a 1 plus. He loses that 1 valence electron. Okay? Now, that's the shape. This shape is called triangular. This shape is called tetrahedron. This shape is called pyramidal. You don't count these unshared pairs up here in the shape. See how that's why that's called a pyramid. You can see why that's called a pyramid. You got 1, 2, 3, 4 electron clouds, but you don't count these shared unshared pairs up here in the shape. So this is why this one's called bent, okay? You just have this angle right here. This angle's 105, this is 107, this is 109, because these unshared pairs push them closer together. So these unshared pairs don't count in the shape, although they actually create it, okay? Now group 17, look here, it's going to be linear because that's the only bonding place it has is right there. Okay, and group 18, no question, doesn't bond. All right, pretty good explanation there. Let's see here. All right, where are we? Let's see. Give atomic number. Boom, 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 boom. The number of electrons. Okay, so you can do this. Where were we up here? Boom. Give name or symbol of element to be able to give the number of protons and electrons. Well, you know that the number of let's see, the number of, what was it say, give a name, be able to give the number of protons. Well, the number of protons is the atomic number. Okay? Number of electrons, it's equal. Okay? Atomic number is going to equal the number of electrons. Okay? The number of protons minus the mass number equals the number of neutrons. Okay, so like if you have carbon 12, you know you have 6 protons. The mass is 12. Well, 12 minus 6 equals 6 neutrons. Okay? 6 protons, 6 neutrons gives you 12 of mass. Okay? Alright? Given the number of protons and the number of electrons, be able to write the formula for the ion. Okay? So if you have a sodium, so you're given the number of protons. So anytime you're given the symbol, you know the protons. So that's 11 protons. And we said, okay, if we have 11 electrons and 11 protons, 11 electrons, it's no charge. But if we have 11 protons and let's say 10 electrons, okay, so we have 11 protons, 10 electrons, so the charge is going to be 1 plus. Magnesium, we've got 12 protons. Let's say we have 10 electrons. The difference is going to be 2 plus, so the charge is going to be 2 plus. And the way you write the symbol for the ion is like that. 1 plus, you write the symbol and the 1 plus. If it's a positive ion, you don't change the ending. If it's a negative ion, like chlorine, let's say we have chlorine. So you got chlorine, it's got 17 protons, and let's say it gains 1 electron, okay? So we got 1 electron plus the 17 protons. We end up with a chloride ion. It still has the 17 protons, but it's got 18 electrons, so it's 1 negative, okay? And that's called a chloride. Change the ending to IDE if it's an anion, okay? So IDE equals anion. It means it's not only it's an ion, but it's an anion, okay? Now, so if you're given the isotopic name, so say a chloride ion, it wouldn't even have to tell you that it's 1 negative, because chloride ions are always 1 negative in group 17. So if it's a 1 negative, it must have 1 more electron than the proton. So it's got 17 protons and 18 electrons. Okay, magnesium would have 12 protons and 10 electrons because it's 2 plus. Okay. All right, let's see here. Where are we? Oh, determine the atomic state. Well, what I noticed in your Well, you know, the protons and the neutrons, you shouldn't have any trouble with this. The protons and the neutrons, location in the atom, the protons and the neutrons are in the nucleus. The electrons are in the energy levels outside the nucleus. Okay? Now, on this excited state or ground state in these, what I noticed she was doing, and I'm not really used to seeing that, but let's say we're talking about oxygen. So we've got a 1s2, 2s2, and then she does stuff like this, a 2, a good example. She did a 2s1 and then a 2p24. And she'd do a 2p5. So what she's got here is a missing electron. That she would call that the excited state. Okay, excited state. Well, the electron configuration is not normal. That's what she's trying to get you to figure out. When the electron configuration is not as you would normally write it, then she's got that as excited state. Okay, know the organization of energy levels, sublevels, and orbitals available. So let's see, let's go back here to this. So here, this would be 1s1, 1s2. Of course, this is the first energy level. That's all there is. Second energy level, this would be 2s1, 2s2. Now this is the p block, okay? This right here is the p block, and this right here is the s block, okay? So this would be 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. This is a noble gas. Total of 8 electrons. 1, 2, and 6 here gives you a total of 8. That's where the octet rule comes from. That all elements are trying to obtain that filled octet. Okay? So then we go down here. This would be 3s1, 3s2, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Then we go to 4s1, 4s2. Now this is 3d. 1 all the way across. And this is 3d10. Then we go back to normal. 4s2, 4p1. I'm getting tired. 4p1, 4p2, 4p3, 4p4, 4p5, 4p6. 8 electrons. So we got 8 valence electrons. 4s1, 4s2, that's 1, 2, and then 3, 4, 5, 6, 7, 8. We don't call these valence electrons, okay? So now we get into here, and what happens right here is these break apart here and come into the D block, okay? The D block. So I think your book has these 2 elements attached down here, okay? But anyway, what would happen is you'd go 5, so this would be 6s1, 6s2, and then you'd come down here to 4d1 all the way through to 4d14, and then you would go to 5f1, so on and so forth, okay? And so this one right here then would go 5D1 to 5D14, and then they would fill like that. And then you come back here to 6. I said D. Jesus, I'm getting tired. This is F. This is the D block. God, sorry. This is the D block. This is the F block. So this would be 4F1, 4F14, 5F1, 5F14, and then you'd come back to the D, 6D1, 5D1. So it goes 6S, 4F, 5D, 7S, 5F, and then 6D, okay? And if you get confused, all you got to do is count the atomic numbers. Go in order of atomic number, right? Stick with the order of atomic number. And the number of electrons, when you're doing these electron configurations on a periodic table, they're going to match the atomic number, okay? All right, that should work there. Let's see where we are here. Boom, boom, boom. All right, protons, neutrons, electrons, energy levels, sublevels. All right, what we got here? Know the shape of an orbital. Okay. Well, the S is circular. The P, well, they call them dumbbell shaped, but what they are is they look like this. That would be PX. That would be PY. And that would be PZ. And then D is screwy. It's got this donut shaped thing, and it's got this shaped thing. And what happens is it falls in the seams of the P's, and there's 5 sets in the D. Okay? It's a little confusing there. So elements 1 through 56, that's going to be what, through barium? Yeah, 1 through barium. So 56 is going to end in 2. I'm sorry, it's going to end in, let's see, 1, 2, 3, 4, 5, 6. 6s2. So 56 is barium, and that's going to end in 6s2. Okay? So what you're going to do then is you're just going to fill in 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, and then 6s2. So you should add that up. That should be right. So that'd be 2. So that'd be helium. That'd be beryllium. That'd be neon. That would be magnesium. That would be 3s6. That'd be argon. That would be calcium. That would be 3d10 would be zinc. 4ps, that'd be krypton, right? 1, 2, 3, 4. Yep, that's krypton. 5s2 would be strontium. 4d10 would be cadmium. 5p6 would be xenon. And 6s2 would be barium. So you add all those up, that should equal 56. Okay? So all you got to do is count these up. If you get an electron configuration on the test, add up the electrons. Say that equals the atomic number. Go to the periodic table, go to that atomic number, and there it is, right? All right. That's a piece of cake. All right, let's see. Go down here to 4. octet rule. The octet rule says that all elements in the main block want to obtain the same electron configuration as the nearest noble gas. The nearest, I like to say it like this, the nearest, the numerically nearest noble gas, okay? Which means aluminum will go back to neon, okay? Phosphorus will go ahead to argon, okay? Ionic bond looks like this. The classic example is sodium. The sodium ion will come here, and it will become a sodium ion with a 1 plus charge because it gives up one electron, okay? The chlorine ion, the chlorine atom, will take that one electron plus the chlorine and produce a chloride ion. Now you have a 1 positive and a 1 negative, and they come together because of that opposite charge, okay? That is an ionic bond. So there's 3 steps. They lose the electrons, they gain their charge, and then they come together because they have opposite charges, okay? If you take a magnesium, it's going to become a magnesium ion, but remember it's 2 plus because it loses 2 electrons. And if you have a chlorine, you're going to have 2 electrons join up with 2 chlorines to produce 2 chlorines with a 1 negative charge, okay? And now you got a total of 2 negative and a total of 2 positive. So they form an ionic bond. And now the formula, of course, is going to be MgCl2. Formula here is going to be NaCl because it's 1 negative, 1 positive. Here it's 2 positive and 1 negative, so you need 2 chlorides. Okay? Covalent bond, the way I like to think about it is there's no difference. And the key here is electronegativity. Electronegativity is the tendency of an atom to take electrons from another atom. So now when we get over to the nonmetal side, say carbon and oxygen, whatever, or even chlorine if you want to, chlorine, is still trying to take electrons just as hard as it is here. Chlorine here wants to take this electron away from the sodium. Okay? This electron right here is this electron right here. Sodium, the chlorine takes it. Well, the chlorine wants to take it away from carbon too, for instance, but the carbon won't give it up. So what they end up doing is fighting over it. The carbon has got its 4 electrons. The chlorine, the 4 chlorines come along, and each one of them wants to take an electron from carbon. It's trying to take the electron. Carbon won't give it up. Carbon won't give it up. So what happens is they end up sharing those electrons, right? It's not the chlorine changed. It's just the carbon won't give it up. So you got 4 single bonds. Covalent bonds. Covalent means sharing. Okay? Now, this only happens in the nonmetals. Let's see what she's trying to say here. Contain only nonmetals, can contain hydrogen, but it is not written first in the formula. Well, what's written first in the formula is the least electronegative element. You got to understand this term, electronegativity. It's the tendency to take electrons, okay? And as you go across the periodic table, the farther you get to the right, the stronger the tendency. So in the formula, the least electronegative element is first, okay? Goes first. So it's carbon tetrachloride. Okay. If it's an ionic bond, it's the metal that's always first, which is the least electronegative, has the least pull for electrons. The non-metal in an ionic bond has got the stronger pull for electrons. So it's always the least electronegative element first in the formula. Okay, so we got down here. A single bond, and what we're talking about is single bond. A single covalent bond is one shared pair. Example would be, let's say, well, you know, a great example is oxygen's got its two unshared pairs up there, and it's got its shared pairs with the hydrogens here. This is a single covalent bond, and this is a single covalent bond. So in water, we have two single covalent bonds. Okay. A double covalent bond is two shared pairs. Best example is carbon. So carbon has got two shared pairs. So each carbon is contributing two electrons there. They're being shared. That's the double bond. And then out here, it's still got two more. So here you have carbon with single bonds. Okay, these are single bonds here. This is a double bond, double covalent bond. Triple covalent bond is going to be like nitrogen. 1, 2, 3, 4, 5, 6. That's three shared pairs. Okay, so each nitrogen put 3 electrons in here. Okay, so that's 6, and there's a total of nitrogen has a total of 10 valence electrons, so each nitrogen's got 2 more stuck out here on the side like this. Okay, so you got 2, 4, 6, 8, 10 total electrons. This 3 shared pairs is a triple covalent bond. Now, a double covalent bond is stronger than a single, and a triple is a stronger bond than a double. Okay? That's a little something for your information. Alright? What we got down here? Double, double, triple. Okay? Non-polar. Alright, so if we have two atoms with exactly the same electronegativity, then we have no pole. Okay, for instance, if you have an oxygen, okay, you've got 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So these will be spread out like this. That'd be a double bond right there. But because we have two oxygens that are covalently bonded together, they both have exactly the same electronegativity. So the electronegativity difference, and it's the key is the difference, equals 0. So that is non-polar. Okay. Now, if you have oxygen like this bonded to hydrogen here and hydrogen here, now this bond, because the oxygen is more electronegative than the hydrogen oxygen has a 3.5 electronegativity. The hydrogen, I believe, is 2.5. Okay. So the hydrogen, the single electron from the hydrogen is being pulled up there towards the oxygen, okay? It's pulled towards the oxygen. So that, in addition to these two unshared paired electrons, leaves that region up there negative compared to the rest of it. Each hydrogen, the end of each one of these bonds, The hydrogen end of each bond is polar, which leaves a polar region in the center down this end. So when you talk about a polar bond, and it only happens in covalent bonds. If the electronegativity is great enough, remember the electrons gets transferred, and that creates an ionic bond. But in a covalent bond, if the electronegativity is greater on one atom than it is the other, then the electrons get pulled more in that direction, and that makes that side of the molecule negative compared to the other side. So this is called a dipole. And all it means is two poles. That's a positive and a negative pole, okay? And that is a polar molecule, okay? This is a nonpolar molecule. And I think the key is, let me see here, I think it's if it's less than, if the electronegativity difference, let's see, the I gotta look it up on my chart, but it's electronegativity difference, ENCE. If the electronegativity difference is less than 0.4, then it is nonpolar. If it is greater than 0.4, how do we see this? Greater than 0.4, but less than 1.7, it's polar. If it's greater than 1.7, it's ionic. Okay, and that's just a basic rule. But this is all based on electronegativity difference. And electronegativity is the tendency, well, the way I define it, she's got to define it a little bit different, is the tendency for an atom to take, I'm just going to say electrons from, and I'm going to call them adjacent, you know what that means, nearby, from adjacent atoms, okay? So if it has a strong tendency to take electrons, then it's got a high electronegativity. And if the electronegativity difference is great enough, it'll actually take it. So if it takes the electron, then you have a negative ion and you leave a positive ion. They come together. That's an ionic bond. But if it can't quite take it, then the bond can be polar like this. Okay. Now I showed you on that thing there with Lewis dot structures. Let me go back over here. Lewis dot structures, okay. So Lewis dot structures, if we draw the X here, the Lewis dot structure for everything in group 1 is going to look like that. It's got 1 electron. Everything in group 2 has got 2 electrons. And remember, these electrons are negative, so they're going to repel each other to the max. Everything in group 3 looks like this. Okay? Everything in group 4 looks like this, tetrahedral. Everything in group 5 looks like this. You got a shared pair up there, boom, 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 5 valence electrons. Everything in group 6 has got, they're paired up on the top, and they got 1 there, okay? Group 7 is pair, 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 and 1 electron, okay? Group 8 is 1, 2, 3, 4, 5, 6, 7, 8, okay? Now, let's say when a group 7 electron comes up here, let's say a fluorine, and it's got boom, 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 boom. I'm going to take one of those off of here. Okay, I'll take one off of here. So we got 7 valence electrons. And then let's say we take a hydrogen over here who's only got 1 valence electron. Boom, that's the bond. That's the Lewis dot structure for that compound, okay? That's the Lewis dot structure. Let's take a carbon here. And the carbon's got 1, 2, 3, 4, okay? I'll draw the hydrogen in blue this time, okay? So we got a hydrogen comes along, he's got one electron. Another hydrogen comes along, he's got one electron. Another hydrogen comes along, he's got one electron. Another hydrogen comes along, he's got one electron. So we have 4 covalent bonds. That's the Lewis dot structure. And remember, that Lewis dot structure, see, we got the, looks like this, looks like a tetrahedron. When you draw these elements out here in their groups, same thing. Let's take nitrogen, okay? So we'll take nitrogen up here. So nitrogen looks like this. It's got a shared pair here, electron here, electron here, electron here. So let's put hydrogen on top of this baby. So hydrogen comes here, got an electron there. Hydrogen's got one electron there. Hydrogen comes here, one electron there. This is called pyramidal, okay? And you can see why. There's the pyramid. 3 covalent bonds. The reason this isn't stretched out here like the carbon is because this unshared pair of electrons pushes these single electrons down. Okay? You might have to call me and ask me about that. That gets a little bit hairy. Well, the diatomic elements. Let's go back over here. The diatomic elements are the gases. These are the gases in the upper right. Plus bromine and iodine and hydrogen too, okay? And so what are they then? They're hydrogen, and then you start with nitrogen, then oxygen, then fluorine, then chlorine, then bromine, and iodine, okay? And diatomic means 2 atoms, okay? And they are so electronegative that they bond to themselves, okay? Now, naming, you might need to talk about that too, but given the name of an ionic compound, write the formula. Well, let's say magnesium. I bet you have this one. Magnesium chloride, okay? Well, what you got to do is go back to the periodic table, and you know that chloride is always 1 negative. You know that magnesium is always 2 positive, right? So how are they going to match up in such a way they're going to end up with a 0 charge? Well, the easy, down, dirty way of doing it is like this here. That 2 is going down there, and that 1 is going down there. So it's going to be magnesium chloride. The name gives you the formula. Now, you say, well, what about if it's a transition metal and you don't know what charge it is? Well, that's when they use the Roman numerals, okay? Okay? Now, molecular compounds can be a little bit trickier, so they use numerical prefixes. Let's say water, for instance. The real name for water is dihydrogen monoxide. So what does that mean? Di means 2 hydrogens, right? Di is 2, and 1 oxygen. Okay? How about carbon tetrachloride? Well, you know, you got carbon. Tetra means 4, so you got 4 chlorines. So it's carbon Cl4. All right, let's see what we got over here. Let's see here. Okay, so Okay, nonpolar means it is less than 0.4, the electronegativity difference. Okay, it's all electronegativity difference. And that means that you take the electronegativity of one element and you subtract it from the electronegativity difference of the other, and the difference from the electronegativity of the other, and the difference is what we're looking at here. So if it's less than 0.4, it's nonpolar. If it's polar covalent, okay, it's between 0.4 to 1.7. That's polar covalent. And if it's ionic, it's above, how do we say that? It's above 1.7. Okay? How do you figure out which one's most polar? Again, it's electronegativity difference. The greater the electronegativity difference, the more nonpolar it is. How polar is it on the periodic table? Look here. The farther apart they are on the table. So if you have a bond between fluorine and oxygen, it's not going to be as polar as the bond between fluorine and nitrogen, which is not going to be as polar as the bond between fluorine and carbon, okay, which is not going to be as polar as the bond between fluorine and boron. And then pretty soon, like right here, what happens is they go ionic because the fluorine takes the electron. The fluorine can't take the electron from the oxygen, the nitrogen, the carbon. But when it gets any farther to the left, it takes it. So we have less polar, more polar, more polar, more polar, and then finally ionic. And so the farther apart they are on the periodic table, the more polar they are. And you got to remember, if it goes from one side, any of these metals over here, any of these metals bonding with any of these over here on this side, they're going to be ionic. They're past polar. Okay? When we talk about polar and nonpolar, we're only talking about nonmetals bonding with each other right here. Okay? So what's more polar, nitrogen and oxygen bond together, or nitrogen or oxygen and carbon? Well, the oxygen and carbon is a more polar bond than nitrogen and oxygen, right? The nitrogen and hydrogen is less polar than the oxygen and hydrogen. And that's less polar than the fluorine and hydrogen. Okay? So the farther apart they are on the periodic table, because electronegativity increases as you go across the table. Okay? Let's see what else we got. Boom, boom, boom. Okay, we talked about that more polar and least polar. Polyatomic ions, you're going to have to work on those. You're going to have to memorize those, okay? Just like I told you in high school, okay? But where do I see polyatomic ions here? You'll be given this sheet showing you the electronegativity difference. Where did I just see that about polyatomic ions? How you do Lewis diagrams for polyatomic ions. Here. So let's say, for example, we're going to look at carbonate. Okay, so let's say we got a CO3 with a 2 negative. Okay. Well, we're going to draw a carbon here. We're going to put the 8 electrons all the way around it. Boom, boom, boom. Okay. And so we're saying, is this the correct electron configuration? So we're looking at this, and we know that we're allowed to have, for carbon, we're allowed to have 4 electrons. For each oxygen, we're allowed to have 6. And plus 2 because of this charge here, okay? So we get to have 2 extra electrons in here, okay? So we have a total of 8, 16, 24, and 2. So we have a total of 26 electrons. That's what we've drawn here. 8, 16, 24. Whoops, 26. Yeah, 26 electrons. And how many are we allowed to have? We're allowed to have 4, 10, 16, 22, and 2 is 24. Okay? So we got too many electrons, right? We got too many electrons. So we have to get rid of one pair of electrons. Right? 4, 10, 16, 22, plus the 2 here, we're allowed to have 24. And we have 8, 16, 22, 24. No, that's right. So that's right. So the way we draw it then is boom. 2 negative. Okay. If we were going to draw water, remember we'd try to remember our shape, and those are the electrons from the from the oxygen, and then we draw the hydrogens down here. I mean, these lone spots are the only places that the bond could be. So we draw this, and we have 2, 4, 6, 8. So the hydrogens are each sharing 2 electrons. That's what they want in the first energy level. And this oxygen gets to play like it's got 8. 2, 4, 6, 8. Okay? And so we're allowed how many electrons? We're allowed 6 for the oxygen, and 1 for the hydrogen, and 1 for the other hydrogen. So we're allowed a total number of 8. And that's what we got over here. Okay? If it's an ion, you draw it like that. Anyway, I think that's a start. I don't know. I hope that helps you. I'm going to try to put this thing online for you tonight. All right. Hope it helps.